pretty much everything you can think of that humans do can be done by biology. And we're in a situation now where the world is in absolute turmoil, climate change and loss of diversity and habitats and species crashing. And we have to stop that, right? And so I know paradoxically, although people are fearful of synthetic biology, or some people are, it may actually be the way forward to actually preserve and conserve nature as we know it. And we're going to have to find a way to kind of preserve natural organisms whilst also very carefully and thoughtfully creating synthetic organisms that can do stuff that's useful for us in a sustainable way.
The effort here is just to really get real insight into synthetic biology, but also not the normal thing that you just get that's like boring. It's like just, you guys could disagree, you can agree, but let's get to the edge of what this thing is. So Adrian, why don't you start off with just, what do you think the future of healthcare is with synthetic biology?
I'm Adrian Woolfson. I'm a physician scientist who's also an entrepreneur and has been fascinated by, if you like, the philosophy of biology for most of my life. Synthetic biology is basically looking at biological systems as machines that can be engineered and redesigned in order to go beyond the structures that evolution has created. So it really involves understanding the rules and the laws which govern how those machines are put together, those biological machines, understanding the inventory of the components, and then kind of working out how those components work together to produce the phenomenon that is the organism of the species. I think the key is to understand that there are about 5,000 diseases, so-called monogenic diseases, where the kind of paradigm of thinking about the body as a machine made of components works very well. And you can fix broken components and thereby fix the disease, right? The problem is that most diseases don't work like that. They're caused by, I would say, problems with the system. So I think the future of medicine is, we're going to hit this glass ceiling when we've fixed all the easy stuff, the monogenic diseases, and then we're going to be into the difficult stuff, which is complex diseases, which are caused by multiple genes. And then we're going to be faced with the problem is how are we going to deal with that? And it may turn out that ultimately the only way to deal with that is to basically rewrite genomes, But obviously that's going to cause a lot of ethical problems. So the challenge will be is how do you fix it without rewriting genomes?
You say it's caused by multiple genes, but right now, do we know the genes, Eli, or do we need to have a new, deeper understanding of what's happening?
I'm Eliah Spencer. I'm a physician scientist. I'd like to see us realize our full potential to develop resilient societies, and I'd like to be there working on it with everybody. There's a whole bunch of things where we know the genes, the easy ones, the one gene, one disease, and those are going to get knocked out pretty quick. Then there's a whole bunch where we know there's a disease and we know there are genes, but we don't know which ones. It's more complex than that. And I think that does take better diagnostics, which is going to be both deeper sequencing and understanding what happens in our bodies, and then AI to kind of help us read the book. Just having the alphabet's not enough.
Andrew, does it make it more complex, this reading of the genome, to understand how these things work together? And how does epigenetics complicate this level of understanding?
I'm Andrew Hessel. I'm a microbiologist and geneticist, and I want to see all living things become programmable. I'm not a human biologist. I'm a microbiologist. So I'm taking a very different perspective on some of this, because for me, it's very bottom up. And we are already at the point now where we can read complete genomes of simple organisms like bacteria and viruses extremely quickly, have really good knowledge of how they're organized. And of course, we're already using synthetic genomics, the ability to make these genomes, from scratch in the field, in practice. So we're going to learn an incredible amount about biology by starting to program it bottom up. And will we be able to fix diseases? Absolutely. This is one of the most powerful and broadly applicable technologies yet.
Certain conditions like Huntington's is one gene. If this was simple, how would we go about interrupting this one gene? It's just if you have this, you've got the disease.
Well, we can make a program to correct that disease. Part of the challenge is how do you load that program into a network like our bodies that have 40 trillion cells.
Yeah.
That's the tricky part.
I mean, Adrian, how do you do that?
Well, with simple monogenic diseases, I mean, you can use basically gene editing. You can either edit things in or edit them out or change how they're switched on and off, put in new copies of the gene which are corrected, So I think that's really quite an easy fit.
But how will artificial intelligence change this discussion, and how will you apply it, Eli?
In some ways, it changes everything. I think since we've had biology and some understanding of how to engineer it, and call that synthetic biology, and we've done a lot. We've read genomes, we make new organisms today. But when you add in AI, you really just completely fundamentally change the approach. You can be using bio AI you asked, how do you deliver a change of a gene to a human? Sometimes we'll use a virus to infect human cells. They spread throughout the body. We might use nanomachines in the future. This concept of a virus or a bacteria or even a human, this all blurs when you take control of the technology. And it's the writing component, the physical changes like CRISPR, et cetera. And then it's the, what words go into your poem's story. And that's our intention plus AI. And that's where this thing gets totally unlocked from, how we handle our healthcare to our sensing to anything else you want. It's sort of when it becomes nonlinear.
Adrian, your first kind of statement, you said, but, it raises ethical questions. And so as we're in this moment in time where, again, there's more and more fear around technology, around AI, certainly, and you hear a lot of that, how do we bring the public along with us in this, what could be such an extraordinary advantage to the human condition? I think it's a narrative, and that's part of what we want to do here. What is the story we're telling about this ability or this potential technology?
I don't want to use hyperbole, but this could be the most powerful advance in human history. And I'm going to steal Andrew's on the phone, so it's not stealing. He talks about life and biology being the most important technology around and the only one that we didn't create. When we take control of this, it's almost a Pandora's box. But to go to your question, people don't understand this yet. So it's a black box, which means it's both fanciful and very scary. And so I think we really have to bring the public into the conversation authentically. This is not so complicated that people can't understand it. We can really get it. We need to have honest discussions about it. It's also not easy to sort of just talk about. And so Andrew's talked about creating very safe synthetic biology pets, or even doing this in computers. We need to start to get our brains around something really new. It's a little bit godlike. And so the first ethical standpoint is don't do this off in a room by yourself. That means working with the public. And the second is maybe trust, because the public is both potentially going to come up with some of the bad ideas, but clearly this is a distributed problem where we all have to help with preventing the bad stuff. So the first part of the ethics is really getting people on board, I think, but realizing the magnitude of the problem. This is massive change the world positive, massive change the world negative.
We've seen that sort of developed with AI, where we're getting a lot of the dystopian vision of AI. We don't hear enough about the positives that it could make possible for us as humans. Do you see that challenge out there, Adrian? The idea of how do we talk about this? How do we communicate these ideas?
Yeah, it is a challenge. And the public is really not aware of the magnitude of what's going to happen, right? I mean, we're basically facing a future in a good way, I think, where there's going to be a convergence between two incredibly powerful synergistic technologies. One is, deep learning AI, which is able to look at huge biological data sets, and which eventually, if given the right information, will be able to infer the generative rules of biology, the rules of life, how you build particular types of organisms, like an author rather than a plagiarist, right? And the second is going to be technologies to write whole genomes, right? So you need to be able to design life, and then you need to be able to write it. And we're actually exponentially improving both of those technologies. So I think the implications of this are quite astonishing and hard to comprehend. And sure, yeah, there needs to be a hugely increased awareness of that. And like every technology, there are good and undesirable aspects of them, but, you can't ignore them. I mean, we can't uninvent AI or the ability to write genomes. In fact, humankind has to develop these. They have a responsibility. That's being human is about inventing secondary worlds, right? That's what we are as a species. And as is often said, fire is a dangerous technology, right? If used inappropriately, you can burn down cities, you can harm people, but you can also use it to cook your breakfast, right? It's up to humans how they decide to navigate these technologies. The technologies themselves are morally neutral.
Andrew, Adrian was just saying there the difference between being an author and being a plagiarist. AI helps you be the greatest plagiarist in the world. Does it also help you be a great author in and of itself?
First of all, I love the intersection of AI and biology because we can't read the executable code of DNA. Like it's a language that AI can interpret natively and manipulate natively. So we're already seeing AI be used to reverse engineer the form of a protein based on sequence. That's been amazing, a huge holy grail that's really led to a golden age of protein engineering. And now it can do annotation of new DNA incredibly well. I think AI in biology is going to be a massive accelerator. The problem that we're having right now is it's still relatively expensive and slow to compile biological programs, to synthesize the DNA and get them running in a biological system, whether it's in a tube with a cell-free system or in a cell like a bacterium or even a human cell. So that's the area that I've been working on in trying to, how do we accelerate the ability to compile these programs and make this whole thing move faster? That being said, we're going to have a new digital architecture to manage all this, because it's really the democratization of the biotechnology industry, which, until now has been pretty constrained to big players and academic institutions. And all of a sudden, it's kind of like when computers went from mainframes to PCs, where I'm seeing kind of the same dynamics here. And I think it's going to take a whole new architecture to do this right and safely in a way that doesn't freak people out and brings in a whole new community of programmers, programming cells now instead of computers. So an incredibly exciting time.
When semiconductors came in, there was incredible, huge battles between giant companies that went on for 5 or 10 years, and you're implying a new industry that's going to have to be created. How are we doing about setting up rules for companies to cooperate? Are we going to stumble into that same problem?
We're going to stumble into that same problem. We're seeing the test version of this in trying to get ahead of AI, or at least be moving as quickly as the technology is moving. I'm not sure there's a real other analogy for life. Like the difference between life and nanotechnology, for instance, is mostly one we didn't create. We've essentially created nanotech, but life self-propagates. And so, imagine if I could buy an iPhone 18. What's the business model behind the iPhone 18, Eli's iPhone 18, when it self-propagates? And in fact, so that I could hey, I just got this new seed phone, and I go over to Andrew's and we put water in it and it duplicates in 24 hours and he's got a phone. And then we throw in some particles of some sort and the phone grows wings and it turns into a drone and flies over to Adrian's house. This is a real paradigm, and this is really where biology can go. We don't have any economic structures that allow us to create products that are self-replicating, that can adapt over time. And so it's not just getting onto the ethics. It's like every dream we have could destroy entire economies. And so I don't think we're really quite prepared for this new dimension of life isn't just programmable and we can do almost anything we want. It could be giftable. It could spread forward. I'll end with, we used to have vaccines that spread. The Salk polio vaccine was something you gave to people, and then if they were nice enough to have 30 hands or pooped, they could spread it to others. It was a positive feed-forward vaccine. We don't allow that today. We said for safety, but actually the marketplace isn't very comfortable with cures that spread themselves. So I think there's a lot to think about, positive and negative here.
So Adrian, how do you think about that?
Well, I immediately thought about the butterfly metamorphosizing from a caterpillar, right? I think the analogy there is perfect. What an extraordinary event, right? To turn from this ugly little featureless caterpillar into this magnificent flying butterfly, right? Imagine if an iPhone could do that, right? And why not? So I think the future is all about making biology into predictable engineering material, which will impact almost every area of life. We'll be using biocomputers, biomaterials, biofuels, bioenergy. Everything will grow houses rather than build houses, right? But all of that will rely on the ability to be able to actually design biology. And that goes back to what I said about the rules of biology. Hipparchus, 2,000 years ago, was the first person really to mathematicize nature by forming a map of the visible sky, right? And unfortunately, biology to date doesn't really have any kind of, laws that are analogous to the laws of physics that can send spaceships to Jupiter or Mars. And that's what's missing in biology, is those types of mathematical laws. And I think AI will get us there. I mean, like Andrew says, AI can predict protein structures, using that program AlphaFold. But even AlphaFold doesn't really know how to do it, right? It is able to kind of do it, but the actual rules are hidden somewhere in the kind of network of the deep learning, right? But isn't gravity a bit like that too, right? We don't really know how gravity works, but we can model it, and by modeling it, we can do a whole load of things, right? So I think the key is to unlock those generative laws, which may not be universal. The laws may be specific to species or groups of species like vertebrates or whatever, right? And like a yeast, for example, lacks a lot of the higher order folded structures of chromosomes that we have, right? So it wouldn't make sense to argue that the yeast does computations in the same way as we do, right? So there may be separate languages within biology as well, right? But at the end of the day, drilling into those languages is what's going to enable us to do stuff using biology and to make machines more like living machines, human-made machines, more like biological machines.
Physics has universal principles. Are we looking for these universal principles in biology, Andrew? And do we know some of them so that we can use them, or are we still in a quest to sort of understand how things work?
I'm trying to answer that question myself. But again, I always go from a bottom-up perspective. What I'm seeing right now, like E. coli, the bacterium E. coli, which is in all of our bodies, has been a model organism, and it has taught us an incredible amount about how cellular life works. And it's led to multiple Nobel Prizes. What I think is going to happen here is that E. coli is going to become the first digital model organism, because we sequenced it in 1997. We've got huge data sets on this particular cell. I think it's safe to say that it's the most studied organism on the planet. I think it's going to make an incredible digital twin accurate to the atom. And we're going to get those dynamics simulated in a cellular environment. And I haven't seen a cellular environment simulator yet, one that with accurate physics where you can just throw a couple of existing proteins in and they interact as they would in a living cell. But I think we're going to get there. I think the visuals are going to be stunning. Like I can imagine guided tours through E. coli's metabolism playing in Las Vegas's Sphere. I can see that, and I want it. But also, the genome of E. coli is only 4.6 million base pairs, which is why I'm championing a 5 million base pair synthesizer, so we can get to build E. coli from scratch. Anyone can, using like synthetic biology in a foundry. And I think that's going to be this massive pile-on scientifically, so that we crack the code of this organism, and the digital twin becomes basically a predictable and reliable simulator of the actual living organism. Now, maybe that's like, I see this happening.
I might just add to that. Yeah. So Drew Endy tried to do exactly that, to simulate, an E. coli being infected by a bacteriophage, right? And he realized very quickly that actually it was too complicated to simulate for many reasons, due to lack of knowledge and biological complexity. And that's why he started doing what he called refactoring. And refactoring is a bit of terminology taken from computer science, where, you end up with all of this code that's evolved over many generations. And it's a real mess, right? It's convoluted, it's baroque, it's like a kind of Gaudi cathedral. And what the computer scientists do is they sit down and they just deconvolute it and simplify it, right? And Drew Endy realized that the bacteriophage is actually, although it's still very simple, it's actually quite complicated nevertheless. Its genes overlap, etc., etc. So what he did is he made a refactored bacteriophage. He simplified it. And I believe probably that to get to kind of vision that Andrew has of a digital twin virus or bacteria as the starting point, you're probably going to need to get rid of some of that complexity, that evolution built in. Evolution was a kind of a D-grade student, kind of, if evolution was a person, they'd be the kind of laziest person in class. They just kind of, would just do what was the absolute minimum to achieve the task, right? And the result is kind of a convoluted mess, right? So I think we're going to have to tidy up these genomes in order to make them simulatable.
Today's podcast is brought to you by Black Orchid. Step into the mysterious shadows of the Black Orchid Emporium. We cradle the most elusive orchids from the dark corners of the globe. They hold the ghost orchid's ethereal glow, a spectral enigma in the twilight, echoing the cosmos' mysteries. It's perfect for your living room. Marvel at the jade slipper orchid, Vietnam's emerald nocturnal jewel, enchanting the forest with its mystical aura. Dogs and cats love this. In the Black Orchid Emporium, these botanical phantoms are more than just plants. They're enigmatic emissaries from the edges of reality. No credit needed. Get approval instantly, but you must act now.
What does it matter that we can do this to the wider public and people that are watching this? Like, what does it mean that we can do this, and how are we going to wipe it out? Are we going to redo it so that then it can be used by a bad actor? Like, what is the end game with this then, to be able to do something like reproduce or create the synthetic E. coli?
Look, E. coli is out there. Like, it's in all of our bodies. It's the grand old cell that's been around for billions of years. What we're learning how to do, it's teaching us how to program a living cell. It might only just be one cell, generally regarded as harmless. Again, it's a model organism. It's in all of our bodies, but it's going to teach us how to program life. Not complex life at this point. Everyone jumps to human, but that's billions of years down the road. Let's start simple. But it's really going to teach us how to do that. And as Adrian says, how to refactor the code. About 1,000 genes in E. coli. It's got about 4,300 proteins. About 1,000 of them are still unknown function. Like, we don't know all the components of a single living cell yet, but we're going to get there. And Drew Endy, bless him, tried to model a virus infecting E. coli. He didn't have the model for the E. coli yet. So you'll never figure out all the things that are happening. But I think we're going to get there in the next few years. We've already made synthetic viruses, synthetic phage. We're going to get there with synthetic E. coli soon. Well, Eli, you're raising your hand there.
I know the proper way to break in a situation like this. I'm going back. Jesse asked, I think you asked a question about physics and biology and asking if we would come up with rules in biology like rules in physics. So biology is governed by the rules of physics. And what's happening is that we're applying it in a complex enough way that it turns into magic. And so this is one of these chaos and complexity, or essentially that if you get a system of enough complexity, it turns into magic fundamentally. And so physicists like to study things that are simple enough so they can call them physics. And you can write them down and you get the impression that there's complete understanding, right? But we know cosmologists can't oversimplify the universe, but they're still physicists. Maybe it has to do with this sort of the original who created biology problem. I mean, there's deities, potential spirituality. It's been here a while that we think it's a different science, but it's not. It's just that it's been so far away from where we can kind of understand it that we treated it that way. And so why I kind of raised my hand is that we're in this intermediate stage, and we're trying to make the virus simpler so we can study it, kind of what Adrian was talking about, or make the bacteria. And that's what Drew Endy, by the way, Drew Endy is the only scientist I know who got the cover of a famous journal by putting a superhero on it, which was synth-bio man. So I think a few things need to happen in our minds, though, is start to understand biology as physics, and we need to start to apply it to it that way. But it's going to take a while for us to really get a deep understanding, which is what Andrew and Adrian were hinting at. I think AI will help us. But there was one more reason I wanted to interrupt. The other side of this is that all the other things that we see in our universe were either planted here by a cosmic accident or they're made by biology. Even sand is significant amounts of it has mollusks in it. So there's this at the very core, humans as gods. Physics allows us to understand all of this. And the other side is realize what all of this is almost anything we can conceive of can be made by biology. And this two ways of thinking that eventually our physics will lead us to understand a full command of biology, and biology can do anything. My area of study was actually how small parts of biology used quantum mechanics to do things. Biology could open up wormholes for all we know. And I don't think our brains aren't really opening up to this. And I'm not even sure we're used to thinking like this. So I think there's some cool new ways of thinking here.
Adrian, you were going to comment on that?
Yeah, I was just going to say, just picking up on this theme of physics, is that, one of the problems we have right now in the field is that we've got a very good analogy, which I think works very well, of biological systems as machines, right? But I think the mistake people make is they look at them as mechanical machines, whereas actually they're statistical machines. When you get down, size matters, right? So the phenomena that happen at the nanometer scale are very different to phenomena that happen at the scale of, large objects, right? So it's appropriate to use the machine metaphor, but they're not like the kind of machines that humans make, right? And that's a really important point, right? But I also, to Priscilla's point, picking up on Eli's point, as to the utility, why does it matter that you can model an E. coli? It matters because, like Eli says, pretty much everything you can think of that humans do can be done by biology. And we're in a situation now where the world is in absolute turmoil, climate change and loss of diversity and habitats and species crashing, and we have to stop that, right? And so I know paradoxically, although people are fearful of synthetic biology, or some people are, it may actually be the way forward to actually preserve and conserve nature as we know it. And we're going to have to find a way to kind of preserve natural organisms whilst also very carefully and thoughtfully creating synthetic organisms that can do stuff that's useful for us in a sustainable way.
I love that because it sort of piques the curiosity, right, to the public. Is there an example of something, Adrian, that we could begin to solve a really complex problem within the enormous magnitude of climate change? What is something, even though we can't do it yet, what could be?
Yeah, there's a load of things like, plastics, for example. You could make bioplastics. I mean, there's a company right now as well making food packaging out of biomaterials, information storage, right? I mean, there's huge amount of energy expended to support information storage. And if you stored information in DNA, there's a huge streamlining in that respect, right? Food production in terms of the production of meat, for example, right? If you were to make biomeat, you'd be chopping down a lot less trees in the Amazon, So I think that by embracing synthetic biology, we could very rapidly have a huge impact on the whole kind of climate destruction phenomenon.
I just think this is an area where it can start now, and things we do today can have an impact while we're extending our horizon a little bit to have the bigger things. For instance, the way climate remediation works today, for the most part, is that our biology on our planet still does a lot to buffer us. Trees still grow. These are carbon sequestering trees, right? Algal blooms still happen. And so in the near future, instead of massive, crazy hacks, we might just upskill some of the planet's natural ways to take care of itself, which would buy us enough time to maybe ethically figure out some bigger games. And so almost everything we're seeing where there's something positive, biofuels, carbon sequestration, novel energy sources, we don't even have to transform the world. We just have to upskill just a little bit some of these processes. And this is where I think, going with where Adrian has gone in your question, this can have a massive impact today, right away. And people could probably grasp it pretty easily.
Even within that, we say, well, we could grapple with the ethical considerations. Right now, there's not even really any infrastructure in order to be able to grapple with the infrastructure. How do you see that happening, the ethical implications?
So in most of the places where, what's the right word for this? Advanced synthetic biology research is happening. So in all of the academic centers that do that, we have local ethical boards. We call them IRBs, right? The IRBs talk to each other around the world, and there's some really good thinking about how basic research is being governed. So in the universities, in some ways it's slowing it down a little bit, but it's thoughtful. Then there's a number of, I won't name them because I'm going to get them all wrong, but there are individual countries that have governing bodies that are working on these problems. And there are a number of, at least the number that I know of, really high level, coming up with everything from the ethics of novel organisms like these new mosquitoes that can take out other mosquitoes, gene drive, to some of the discussions about gain of function research. You might have heard that term associated with a virus that was around. So I actually think we may not hear it as much because people don't know what synthetic biology is that much anyway. So they certainly don't know that there really are a lot of people thinking about the intersection of ethics and biosafety. And it's come out of the genetic revolution that happened with Spencer's work and some of the work that Andrew has really been there since the beginning on the genome read. That infrastructure is moving into this new place. What I think, and I've spoken with some US government officials, is people really don't realize how advanced we are already. They think this is coming. It's here. And that means also that for some people, it's here without any ethical regulation. Other places, we always say other places, and that's where we're really not caught up, is we're sort of thinking about how to slow ourselves down a little bit. Like we don't want to modulate humans yet too much. We're starting to do with cystic fibrosis and sickle cell disease. But I think we're thinking about that right. Where we're not really smart is thinking about the people who are not going to do it your way. And that's called defense thinking. We don't like to do that, but we really need to, because this is where the dark side of this is something we're not really grappling with, to be frank.
Looking down the road 20 or 30 years, what do you think it looks like, this kind of change? You know, we always hear this conversation like, well, what will artificial intelligence change? It's like, it's going to change everything, right? Like, what is it not going to change? You know, is a better question. You know, what are your thoughts on where this goes?
So life, as far as I can tell, touches every industry and everything we do. So I think it's going to have huge impact on the world. I think we're going to replace a lot of the extractive processes that we've done with natural resources and replace them with much more intentional, precision engineered resources as we start to build biology. So I am very much an optimist in this. And I think our guide to how it evolves over the coming decades is really looking at the other programming industry. Here, we're talking about programming life here. The other programming industry has been our history of, you know, these devices and computing. And I think we can actually learn a lot from the history of computing to kind of understand the dynamics that are coming in programming life and chart a course and avoid the major pitfalls. Like right away, we know that if you're going to use digital tools to program life, you're going to need some biosecurity. You know, we've got a $200 billion cybersecurity industry now, but I don't think anyone really feels like their computers are totally secure. I think we need to do a better job with the programming life stuff, kind of bottom up. And the only way that I know how to do that personally is transparency. Like, I'm a big fan of open source biology. I've just talked about, you know, making E. coli an open source model organism, digital organism. I think we have to make it playful. If you look at the early days of computing, there were a small number of business applications, but really it was toys. It was the fact that millions of kids went out and got a VIC-20 or a Commodore 64 or a TRS-80, and they just started playing with it. And that's where I think we need to put a lot more effort as a science and engineering community today globally. Like, because right now we're seeing top-down concerns about biosecurity, US, China, and other places, and non-state actors, and how can I think we just have to start making it safe for kids and anyone to start learning a little bit about this. Not doing it at home, because you just can't get the same quality control at home. I'm talking about robotic labs where you can learn to start to program bacteria and phage, harmless to us, in using these digital tools in reliable ways. And I bought an Arduino the other day just because here's a microcomputer, a processor that, you know, you can connect to inputs and outputs, sensors and actuators that kids play with, and it gets them started in robotics and automation and programming. I want E. coli to be the Arduino. I want it to be something understandable and safe. And once we can start programming one bacterium, we basically can program them all. Okay. And once we can program one virus, we can basically program them all, which is why we need to get a lot better at biology and antiviruses and vaccines and transparency around this type of engineering work. We're still arguing about the source of a virus that kicked our butt, 4 years ago. And that just is not the way to go forward.
So, Eli, what do you think the repercussions in the next 30 years are for health? You described a couple of conditions that we're starting to use these interventions in, but what do you think it does for, we talked about the digital twin. The digital twin could be a place where you could experiment and see if an intervention might work. But what do you see the vision of this being?
Well, 30 years. I mean, there's a lot bigger difference between asking the difference between what would happen like in 1824 and 1854 and 2024 and 2054. So one possibility is nothing happens and we go backwards because bad politics, bad economics, and we're distracted. Maybe just setting up the boundaries. The other one, not too fantastically, is 30 years is a long time. So if we really, the FDA is very interested in improving the speed of how things get through, and digital twins make it easier to find out if something's safer. So I'm going to go to the hopeful, bright future and maybe where we started. So Adrian's list of monogenic illnesses is over. You potentially don't get those because it's detected in the embryo and a baby-safe adenovirus is given to mom and errors are corrected before you get born, programmed. This all gets very weird because we know about programming early life. There's another word for it, which I don't even like to use. So there's some ethical considerations here, but there's no reason that today's humans need to have these diseases. And there's no reason it needs to be expensive either, right? I like to use the term declarative biology. We should simply declare something and it will be so. It's whether or not the money and the economics and the regulation allow us to. So this should not be something for only rich people in Malibu. Sorry, Malibu. This should be something that could be done distributed in 30 years for sure. And we have more cell phones than we have working toilets on this planet. There is no human who cannot access the world's greatest technology today and shouldn't. So those diseases are gone. So then, the episodic diseases, the things that come up in your life, either like a cancer or an infection. Infections should be easy. We should be much better at antibiotics or even having our gut microbiome make antibiotics on demand for us. Those should go away. So I think we're much more in the same way the last 2,000 years was the 2,000 years of infectious diseases. We're really getting the gain of function potential COVID aside. We're actually not dying of pandemics as much as we think. I hate to be the bearer of good news. That should just keep going. And really somewhere fast. I mean, like 10 years, we should be moving to, well, I know it's a little scary, folks, but do you want to do some additions to your body? Make it a little better? And we're going to have the same politics play out. Conservative, and all said with love here. People who want to conserve the way we've done it before will say, hey, look, you know what? This is really scary. Let's not create more species of humans quite yet. But then people are going to say, listen, I hear you, but I don't care. And they're going to do it. So what I think is very likely is all things will be true. In 30 years, there will be people who, despite rapid advances in technology, have no access to it. I don't know who they are, but we will find ways to leave people behind. They're going to be angry. But then for a good chunk of the population, I think most of the things how many are on this call? 6 of us together. We're all sort of like, we have at least one health problem at our age. We shouldn't have to deal with that. Those should go away. And so the last one is how much we're changing and becoming transhuman and post-human and all these new things. And I don't want to make predictions about that. That's more like what art will look like in 2050. But we really should. We should start to see 30 years is long enough out that with any reasonable work, we should knock down the majority of the diseases we talk about today.
It used to be in the circus when they would have conjoined twins, or even now, you cut the conjoined twins apart and one dies, right? Because we can't conceive of a world where people could live like that. And now autism, if you could cure autism, would you cure it, Adrian? Or is autism another way of being human? Is there an inherent difficulty in understanding what's human and what's not?
Yeah, well, there is this concept, obviously, of diversity, and this has been a big issue, for example, in the deaf community, who really don't see deafness as a problem, and they've actually got their own culture and sign language, and a lot of deaf parents want their kids to be brought up deaf. They don't want to correct them in utero, and so I think there's some really fundamental questions about what it means to be human, right, and the degree of diversity that term, encompasses, right? And, obviously we know that, not so long ago, there were multiple different species of human, which for one reason or another went extinct, right? And we have no idea what their humanity looked like, right? What would Neanderthals have been capable of achieving? What would their morality have been like? What would their ethics have been like? What would their creativity and culture have been like? We have no idea, right? And if you believe in the process of evolution by natural selection as being what it essentially is, which is a very historically contingent kind of ad hoc process, then, as Stephen Jay Gould said, were you to replay the tape of life many hundreds and hundreds of thousands of times, the probability of you ending up with humans that look like us and think like us and talk like us is almost infinitesimally small, right? In other words, we have no intrinsic imprimatur, license to print other than the fact that we're here, right? Chance made us happen, right? So, the way we are is kind of pretty arbitrary, right? So how you define the limits of humanity and what it means to be human is really has to be consensually defined. And I would say that, would I want to be deaf? No, I wouldn't, because I like going to the opera or going to a play or going to hear a band play, right? And I know the value that can add to my life. Having said that, if there are people who have developed their own kind of cultures, which I can't participate in, I'm not able to comprehend sign language and the beauty therein, right? So I'm missing out on that. And hey, it's just as valid as going and listening to music at a concert. So yeah, I think we have to be able to accommodate these other dimensions of humanity. And I think the point, love sickness used to be a disease, formal disease until not so long ago, right? It isn't classed as a disease anymore, right? So I think there's some, I don't think there are any quick answers about this, by the way, but I just think generally speaking, we have to be open to realizing that the diversity around us is an intrinsic part of being human. And we have to tolerate it, accommodate it, and cherish it as well.
Is there anything unique about human beings? Is it our love of Beethoven? Is it our love of mathematics or understanding physics? Is there something in there that's intrinsically human that makes us curious more than apes or parrots or whales?
No, full disclosure, I come from a little bit of a background that isn't sure that humans are distinct even. Our version of reality has to be very, very distinct and special and unique. We're all our grandmother's favorite son and daughter, but I'm not even sure we're distinct as species, like literally at the quantum mechanic level. So let alone that we're special. I think we're going to have to more and more face these critical truths of our lack of separateness from nature, our lack of separateness from the rules of nature, and it'll be both liberating and enlightening as we take out some of that pressure. But also the thing we haven't really talked about here is we have all this new power, and I think we're still at the level of kindergartners in our intellect. And we were kindergartners or 3-year-olds with nuclear weapons before, and kindergartners and 3-year-olds now with cyber warfare. Now we're maybe 4-year-olds with, the most powerful new technology we've ever invented, because this can put a nuclear bomb's power in a 7-year-old's hands. They can go to declarative biology. They can order something online. They could destroy our universe. Where I'm going is, I think our culture needs to catch up to this, to really figure out what our place in the universe is as humans, to come up with some sort of a spirituality or a culture that is beneficial and forward-looking, because otherwise we have new chances to kind of destroy ourselves. Is our culture advanced enough to deal with this? Maybe this will help us better understand what we really are, and we'll face it.
I love that. And that's the part that you're talking about that to me is the most worrisome. And we know there's, it could be the best of us and the worst of us, and unfortunately, history has proven we don't always, as a group of humans, make the best choices for the group of humans collectively. So it's going to need that oversight that Jesse was talking about, and we're not even able to do it with AI. I think we talked about that the last time we all talked. So the question is there something now that you all think you can be doing, going and speaking in front of whatever these, and maybe you're already doing it, these big commission, these global conferences? Is that all also happening as you're doing this incredible work?
yes, there are top-down efforts ranging from the UN and the United States and other governments looking at how do we regulate this? How do we put in guardrails? How do we control it? How do we do it safely? And multiple organizations. I'm taking a very different point of view right now. I'm taking the point of view of how do we start bottom up? Like literally, this is going to be something that we want to teach our kids, how to program a simple cell to do something incredibly easy. Like the first experiment with an Arduino is make an LED blink. The first experiment with software is Hello World, learning how to program. I want to keep it at that level and just start working up because, again, this isn't our first rodeo with programming. We know how humans engage with technologies. Most of them are good. A few of them are bad. I think we can avoid the pitfalls, but we simply don't know what the world is going to look like as this technology democratizes any more than we knew in 1978 when the first PCs were kind of becoming available commercially, what it would lead to in the world of computing today. We simply can't extrapolate that much, but it's going to happen. We're going to get really good at programming single cells to do useful things. It's going to generate a completely new economy, just like software and computer hardware did. We're going to tackle some big problems like diseases. My favorite one is cancer and infectious diseases. I think we can eradicate those if we get smart. And our capabilities are going to increase quickly because this time we don't need to build hardware fabs to get to the next level of the technology. We just have to write better code. And E. coli and us aren't that different. We're still running the same code, the same basic cellular system. It's just one cell. We're 40 trillion working as a network. But the difference in it's a 3 billion bit program. We're going to get to that level of programming pretty quickly, and humans will be the last to benefit from that in some ways because we're gonna learn how to program mushrooms or plants and insects and other things long before we really start to manipulate our genome in hugely significant ways. But that's just my perspective.
Thank you. So much to think about.
Yeah, thank you. This is great.
This is wonderful. We're so excited to continue talking and getting this out into the world.